It's my pleasure to welcome everyone. Thanks for joining us this morning to talk about superfluous sign removal in TomTom with Zishan and myself. Okay, how do I? Here I go to the next slide. Right, so we'll talk a little bit about the problem. We will introduce you to our data and our methods and transition to what machine learning we're using to solve this particular problem. First, a short introduction of us and our topic. So speaking today is yours truly and Zishan, who's a data scientist. I'm an engineering manager. And we belong to the same feature team in the ADAS unit in TomTom, where we are delivering signs to the map. So a lot of things can be said about how map making works, but very simplified, a map consists of many different layers and then features to every layer. And our job is delivering traffic signs and traffic lights to the map. So that's what we're talking about today, maps and map making. And in this case, yeah, and in general, trusting maps is kind of importance. So it's important that we keep them updated and as accurate as possible. Right, so short introduction to superfluous signs. What even is that? So a superfluous sign is basically a sign that isn't there, either because it was never there or because it's not there anymore, like in the example that Zishan likes to use, where because there was a meteor that crashed and just obliterated a sign that was there, or maybe a more kind of realistic example where, for example, there was roadworks on a highway and the speed signs were really much lower than usual, and then there's no roadworks anymore, and obviously we don't want cars to think that they should keep driving in 30 miles per hour. Right, so a little bit about our data sources, the data we use to for this problem. So the traffic signs in the TomTom map contains sometimes superfluous signs, sadly, signs that should be removed. They contain a geolocation, and they are matched to the road network. I'm not going to go into detail about the process of map matching, but again, in very simplified terms, a feature such as a map is a feature such as a sign is map matched to, in this case, the road network, so we know exactly what road the sign belongs to. And sometimes this is very simple, straightforward. Sometimes in cities or in large junctions where there's like, many roads and many directions and many different signs, it's more complicated. And the sources we have, the sources that we work with here are sensor derived observations. We like to call them SDO. And these are traffic sign observations by cars. So they can be from various, various cars. They contain geolocation, so we know where the observation was observed. And this data can be very noisy, so that's something that we have to deal with basically. But we have these huge amounts of data that cars that drive around are always generating, and we have to then process this data and make sense of it. And I think Zishan can take it from here and explain what we do with this data then in this case.
Thanks, Julia, for the introduction. So as Julia mentioned that, yeah, the data is noisy. We need to clean it up or make sense of it, aggregate it before we're confident that the sign is actually there. How do we do this? We basically started with a very naive approach by clustering it statically for a fixed amount of time, let's say 7 days or 14 days. But the issues which we faced over there, if the time period was too small, not every road where the less busy roads were included in these wins. So we didn't have, let's say, 50 cars in those wins within the 7 days. Whereas if the window period was too big, let's say like 60 days or something like that, the advantage would be that we'd have all of these roads. So we'd have at least 50 cars going on these roads in 90 days, but it would also have a huge computational impact because you can imagine that there are also busy roads where we have like a lot of transitions or cars driving on these roads every day. So computationally, it becomes expensive. The other disadvantage is you also have some outdated informations. So imagine if you're just looking into the past 90 days and somewhere on the 45th day, the sign was removed. So you'd have this information where half of the time this was present and the other half it was not present. So that's where we thought of the dynamical clustered approach, which is described in the image there. What we do in this case is we say, like, look into the roads and collect at least 50 cars passing through them, but use at least 30 days for clustering. For in some of the busy roads, this 50 cars could be achieved in 1 day, but we do not want this most recent information alone because it could be because of a temporary sign like a construction zone and so on. So instead of that, in such cases, you look back into into the history for 30 days. But there are not so busy roads and very calm roads where you wouldn't find them in the first 30 days. In such context, we kind of increase the time window to 90 days. And even in the worst case that we don't see 50 cars in the last 90 days, and we said that we are not so sure about these roads, and so we don't consider in our superfluous science approach. All right. The click doesn't take me to the next slide. Thanks, Julia. And yes, now that we uh, explained how the signs are aggregated and we come up with the knowledge whether the sign is present or not, how do we actually do the matching? And how do we do the superflow science methods? So we have the map, which is basically, as it says, a map. Then we have the exterior sign, which is present. Now we do what is called a comparison space on the same road segment. So what's a road segment? It's just a big road. Cut them into tinier pieces. It's more convenient to derive information and do a comparison, not from location to location basis, not with geo coordinates, but rather on the road segment wise. Why do we go with this data structure? Because most of our data architecture is based on the road segment level, and we save the information, and that way this was more convenient to get it rolling. So keeping that in mind, what would be a superfluous sign? The first one would be a correct sign. You have a sign in the map, and you have a corresponding SGS sign saying then in the similar road segment. So it would mean that it's a right sign. Where the superfluous sign lead or a candidate would be in the second case where you have the map, but on the SGS sign on the same road segment, you do not find a corresponding sign anywhere on the map. Next slide, please. This works up to a large extent, but it also has some undesired behavior. On the first case, on the left-hand side, you can see that this is what we want. But the undesired behavior, which I was talking about, is the second one. Since a comparison space is the entire road segment, it can happen that a map can be somewhere on the right extreme of that segment. Sorry, the sign can be on the map on the right extreme on the segment, whereas on the SGO it can be pretty far, but on the same row segment. And since a comparison space is row segment, you still say this is a correct sign and not a superfluous sign. Whereas the third case would be all right. Next slide, please. So we use this method, we being aware of the drawback we had, and yeah, it nevertheless produced us good results. We achieved a precision of around 75% for Netherlands, and the metrics here are on the slides. What was next? The next slide, please. You can see that we validated 11,000 leads. And the good thing about having validated leads is we can use this for ground truth as for machine learning problem. And that was a cue to yeah, think of ideas to improve our undesired behavior from the previous approach, which we mentioned before, the one on the right hand side top corner. So we basically wanted to solve this with this machine learning problem. Sorry, with this by phrasing it as a machine learning problem. Next slide, please. Yes, how do we go about this process? So we present this as a machine learning classification problem, where it's a binary classifying, saying it's a if a sign is a superfluous sign or not, and what are the features which we provide to the model to make this classification. Um, Basically, we compute the three nearest neighbors with special KNN. For one sign and map, you would find three SGS signs, nearest SGS signs of the same type and yeah, value, and provide this as a feature along with bunch of other features like along with the distance to the nearest neighbors. You also provide like bearing to the machine learning model, and we expect it to yeah tell us if the superfluous sign is superfluous or not. What's the intuition behind it? If the sign is superfluous, we'd expect there's no corresponding neighbor, so the distance to the neighbors would be higher. And if it is a correct match and it is not superfluous, then the distance would be low. Yeah, instead of we coming up with coming up with this thresholds on our own, the idea was to l- let the model learn this distance threshold for various countries by providing this. And additionally, you'd expect that the bearing information um, for corresponding sign would be the same. They would be facing in the same directions, right? So these are the features we provided to the model. And instead of yeah choosing a best model like XGBoost or like GBM, we use AutoML to basically try out most of them and do the hyperparameter search and the model search and to come up with the best model for our data. Next slide, please. And this was the outcome. Here you can see the feature importance plots. Basically, idea on what was the machine learning model looking into, which features did it consider the most important ones, and the importance is mentioned in the descending order, the top one being the highest. And as you would have thought, eagle distance 1, eagle distance 2, or these are the distances to the nearest neighbors, and these features are pretty important, and they um, the majority of the features which are going into making the decision by the model. For those of you who haven't seen these kind of plots before, on the right hand side you can see the high and low bar. Low indicates blue and the red is high. And if you look into the corresponding row on eagle distance 1, you'd see that if the eagle distance is pretty low, then the signs are classified as low, that is non-superfluous. And if the distance increases, you can see the red spots on the right hand side of eagle distance 1 row, which means that higher the distance, the higher chances of it being a superfluous sign. So it agrees with the intuition and makes sense. And you could also see some other features which I have supplied to the model. For example, confidence is one of them. What exactly is confidence and how do we derive it? It's basically a ratio of number of times the sign was observed divided by the number of chances you had to see these observations. Let's say 50 cars passed by, but you only saw it 30 times, then the confidence would be 3 by 5. Yeah, and that's basically the features which the machine learning model is looking into. Moving on to the next slide. That was the machine learning part of it, and the first method which I mentioned to you, the heuristic method on the comparison space. How do we fit this together, and how is this happening? So we divide this into two parts basically. On the top, you have the machine learning classification model, and on the bottom side, on the bottom wing, you have the heuristic classification model. And you start with these leads, which are generated by individual methods. Then you kind of fuse them, and basically you would have a couple of types of leads where both the methods agree. This would say that okay, this the precision is pretty high. Then you would have methods where the machine learning model says superfluous, whereas the classification say otherwise. And this would be those cases, the undesired behavior cases, which I mentioned before, and so on. And there'd be some uncertainty cases where the prediction is there, but the confidence is a bit low, for example, 60%, and so on. So we basically use these kind of leads and we validate every day. And once the manual, next slide, please. The manual labeling is happening, you can see that there's a feedback loop. And this is more ground truth for us. And the process continues in a lifelong manner where we continue validating and collecting the seeds. And maybe within a week, we retrain the model with a bigger data set, and which would give us better performance on the machine learning models. And we also, as a outcome, we have some leads which are validated and can be removed from the map. So this process is continued until a machine learning model is confident enough, is good enough that we the quality threshold is sufficient for reaching our automatic removal threshold. And once it's done, we stopped retraining the process or the manual validation part. And from this on point onwards, we can say that the machine learning is confident enough to remove the remaining leads which are classified as superfluous. All right, next slide, please. Here you can see that the result improves as the size of the machine learning model dataset increases. So initially, when we don't have any leads for the specific country, we basically use a model which is trained on a previous country, for example, and train them. And initially, it's not so, let's say, um, precise and not confident. And at that part, the heuristic model has higher importance. But we, as we increase the data set size, you can see from when we move from 1800 to 5800, for example, the precision jumps from 70 to 88%. The recall also goes up to 92%. And that's basically the whole workflow. And moving on to the next slide, concluding what we presented here and what we have worked in the last quarters on this is we initially started with a POC where without any machine learning, because we didn't have any ground truth, we started with a heuristic model with humans in loop, use this feedback to iteratively improve our process, also to collect and generate training data for machine learning models. And thereafter, we trained a machine learning model with AutoML, which is complementing this heuristic approach. And using an ensemble of these models, we are able to reach um, uh, a quality threshold where we can automatically learn and remove signs from the map. At least 85% of the signs are removed without any manual intervention. The other 15% is for collecting the uh, the ground truth, basically. And in such a manner, we have introduced a system which is not only achieving good automation results, but is also learning for the entirety of the life. So there's lifelong learning, wherefore, in the future, when we periodically rerun the superfluous signs, because yeah, you don't need to do it very frequently. You don't imagine that the signs keep disappearing next day or so on. But let's say in 6 months, you do this, and there's a reality drift. For example, distance between the two have increased or decreased, and we need the machine learning model to adapt on it. We have this method where we have the lifelong learning with the machine learning model, and which should adapt to the newer data. Yeah, and yeah, that was it. Thank you so much for joining in with us and for your attention. And if you have any more questions, you could please shoot it on the chat, or we are also available on the Slack. Thank you so
Yeah,
much.
thank you so much for joining us this morning. And I don't know if there are any questions that have come in. If there are, we can try to address them now. Otherwise, um, somewhere else. So yeah, thanks for joining us.
Thank you, and bye.